All right. I will begin. Heavenly Father, we thank you for this day. We thank you for the semester about to start. I just pray you bless this class. Encourage your students as they work on this course. Just do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right. So you may or may not know, I'm James Cook. I have an office by the physics labs. Very exciting. DeMoss 3183. I have office hours Monday, Wednesday, Thursday, Friday, 8:55 to 10:30. I have an hour on Tuesday from 10:05 to 11:05, and I have also an hour on Friday from 3 to 4:15. More important to you guys, I have a help session, which is part of my office hours, from 4:15 to 5:15, where in this very room on Friday. So that is a extra help session that we can talk about homework, but not the homework that you're doing, homework that you'd like to do. All right, so I try not to talk about the actual problems I've assigned because the point of those is for you to work them out, right? And but that help session should be, well, helpful. Now, if you can't make it to the help session for various reasons, you can always submit questions by email in advance, and I'll try to answer those. Yeah. That help session, along with these lectures, I try to tape and post on the YouTube, or YouTube as people usually call it. And I have a channel. You saw a link. All that. You know the deal. Any questions about that aspect of the course? All right. We have, if I recall correctly, 3 tests, I think a couple quizzes, bunch of missions. There's a final exam eventually. You need to know stuff there. Any questions about any of that? It's all posted. All right, my apologies in advance for the many weekly announcements I'm sending you. I mean, I always send announcements, but now I'm required to send one every week. So, and it's so if I send you an announcement, it seems like it's odd. It's just because I'm required by the university to send in a weekly announcement. Yeah, yeah.
Are all announcements set to explode at midnight?
Ah, you found it. Yeah, I told Dr. Sprano what he should do is he should make it, if he doesn't want people to read his announcement, what he needs to do, right? Is tell them there's going to be an announcement. It's just going to appear in Blackboard. It's not going to be emailed, right? And in this announcement, there's going to be a secret word. So it only appears for like 15 minutes, but if anybody gets a secret word, they can say it next class. So you have people watching it, right? They find out the secret word, they go to the next class, and they're like, I saw your announcement, I know the secret word. And he's like, go ahead. And the kid's like, Zamboni. And then Dr. Sprano would be like, you just lost 5 points. I hope you learned your lesson. I don't want you to read those. Yeah, yeah. So no, I try to just send announcements that are about things. So yeah, I don't know, whatever. All right, so this is of course about a course in group theory. Today, my main goal is to define a group, a ring, and outline some of the main motivations of group theory. So let me get started on that. All right. So the text, if you will. Textbook, primarily my notes. My notes are born of several sources. Certainly, this book figured large into it. This is Contemporary Abstract Algebra by Galian. I think this is the 5th edition. I think it's in its 10th edition now, which is much more costly. But I have a bunch of problems from this posted. It doesn't matter if you have it or don't. I'm just saying these notes are in part based on that, but the notes should be self-contained. I also, of course, hope at this point that you have watched the prequel 1, 2, and 3, right, where I discuss fascinating things like integers, modular arithmetic, and probably new permutations, right? Okay, so lecture 1. So a little bit on the history of groups. History and motivation of groups. Where do they come from? Why are we talking about them this semester? Where's the trash can? Well, I didn't hit anyone, so that's a victory. Oh, wait a minute. These are all garbage. Someone left these here. Aha. I took time to make sure these work earlier. But you see, this is the thing. I make sure markers work, and then I forget. I come to a classroom, and there's these markers sitting around, like, oh, you can use them. Except, no, they're garbage. All right. So this is a fairly old story, and the story starts with people trying to solve equations like this. ax squared plus bx plus c equals to 0. You studied this probably since middle school, something like this, right? It's a quadratic equation. Solutions to quadratic equations have been known to the, well, civilization for a long time. Babylonians, not mentioning Indians in this talk will bring comments to my YouTube channel. So, I mean, you pick your favorite ancient people group. They have figured out how to solve this in some sense or another, all right? It's there. It's something you want to do to understand things like triangles and geometry and so forth, right? Which is the sort of thing you'd want to do if you were like surveying land. It's just a natural problem to come to if you're any kind of society at all. So this is very old. People know how to solve this in one way or another for quite some time. But then, a couple hundred years ago, we started looking at things like, you know, ax cubed plus bx squared plus cx plus d equals to 0. All right, this is a cubic equation. What are the solutions to that? Do you know? Is there a cubic formula? In fact, there is. It's about a page long, right? And in fact, that formula necessarily involves complex numbers. Even real solutions to cubic equations naturally and somewhat inexplicably involve imaginary numbers. But that's been known since, let's see who did that. I forget these names if I step away from them too long. But certainly, that was solved by Del Faro. It's about 1500. And then Tartaglia solved it around 1530. It was published by Cardano in his Ars Magna in 1545. And then Cardano's student Ferrari solved the Quintic. So the Quintic, of course, would be, you know, one more, right? Well, I can't. Fine. I was not going to write this. Oh, well, it's too late. All right, so that's a Quintic, obviously. Assuming, of course, A is non-zero, right? And, you know, is there a Quintic formula? Yes, there is, in fact, a Quintic formula. In fact, the way these are solved is by doing this trick, and you look at the depressed polynomial. There's kind of a standard technique. It's based on generalizing that completing the square thing you learned in algebra. My wife studied these things in high school where she went, which was Hong Kong. And so not every Hong Kongian high school does that, but she was in a pretty good math program. So you could do that in high school. I mean, you could study solutions to the cubic and the Quintic, and there's kind of a standard. There starts to be a feeling like we could just keep doing this, right? So this was, again, this was about 1545, and that all these things were known, published, all right? And then all of a sudden we got to the fifth order polynomial problem, the Quintic, all right? Something like, you know, x to the fifth minus 1 equal to 0. Now, there's a fifth order polynomial equation you probably could solve. What's the solution? 1, right? 1 is definitely a solution. Are there others? There are 4 other complex solutions that come in conjugate pairs, but you probably can't just rattle those off, right? So certainly it's possible for a fifth order equation to have solutions, right? Polynomial equation to have solutions, but, you know, can you come up with the analog to this thing, right? We know x is equal to what? Minus b plus or minus the square root b squared minus 4ac divided by 2a, right? The quadratic formula. That's the solutions in terms of ordinary squares and square roots and products and differences and so forth. Ordinary arithmetic, a formula, right? Can you find a Quintic formula in the same sense, right? And so people tried after, you know, after Ferrari and Cardano published all that stuff in the mid-1500s. And they tried, and they tried, and they tried, and they tried. And then along comes Lagrange, and we're talking, you know, 1750 to 1800, somewhere in there. he just hammered away at this problem. He tried really, really hard to find the analog of the fifth order quadratic equation, the Quintic equation. And it became clear from his arguments, many of which involved what are called permutations, those. He started looking at permutations on the roots of the polynomial, right? And through these studies, it began to appear like, in fact, it wouldn't be possible to find a general fifth order analog to the quadratic equation, right? But he didn't prove it, but it was kind of in the water. It was starting to appear that way. Then in the early 19th century, about 1813 or so, a character named Ruffini gave a proof, which people still debate whether or not it actually was a proof, but Ruffini basically proved that, no, you can't. You can't have a fifth order. You can't have the analog of the quadratic equation for fifth order problems. And then Abel, I think most people would probably give the credit to Abel. Abel was able, depending on, Abel was able in 1819 to actually give a definitive and standing up to the test of time proof that no, there does not exist a quadratic formula for the fifth order problem, right? And so that was at the age of 19. How old are you guys? No? I didn't do anything that awesome when I was 19 either. I don't know. You guys are past 19, right? Oh, I'm sorry. It's all over. Sorry. I'll shut up. Now, to give you an example, 3x to the fifth minus 15x plus 5 equals to 0. This fifth order equation has no solutions that can be written. You can't solve this one in this sort of way. How can I say this? It's not, to be more precise, it cannot be solved by radicals, right? You can't find a solution in terms of radicals. So Abel was just able to prove, no, you can't do it. The next step was left to this other rather interesting character by the name of Galois. So Galois, in, let's see here, trying to find a date here, 1831. What Galois did was to take the next step. He introduced this idea that to study a polynomial equation, you should think about its set of roots. And you should think about permutations between the roots. Now, I told you Lagrange was already doing that, right? But Galois took it to the next step, all right? And he said, you can look at this set of roots, you can study the permutations between the roots, and you can study the structure of those in basically what we now call a group. All right, the permutations on the roots of the polynomial form a group. And what he was able to say is that this Galois group, as we now call it, all right, if it's solvable, that implies solution via radicals exists. But on the other hand, if it's simple, then that implies no solution via radicals. So the Galois group may or may not be solvable. All right, so I think the Galois group for x to the fifth minus 5, excuse me, good grief, this one, I believe, I think this one has a solvable group, whereas this one, if you were to look at its Galois group, would not have a solvable Galois group, which means by Galois theory, as we now call it, there does not exist a solution via radicals. All right. Now, it does give me joy that this term simple actually has a somewhat deep and technical meaning in terms of group theory, right? It's kind of perverse that we name something simple when that's actually a technical term, right? In contrast, complex numbers should actually be called simple numbers because they're not complicated. They're actually very ordinary, useful garden variety things. But anyway, I digress. Now, we're not going to study Galois theory in here because that's actually next semester. All right, Galois theory, to understand it, takes a lot more development. What we're going to do is we're just going to study this concept of a group, all right? And that group was already present in Galois study. Now, the other place that we found groups in 19th century mathematics was in the study of transformations, all right? Thinking about geometry and taking one shape and maintaining the shape. What are possible ways to take a shape and keep the shape the same while transforming it according to some sort of set of geometric transformations? Those things also form what's called a group, all right? So let's get to it. What is a group? So first thing, actually, I'm just going to put an example up here. Put it over here, keep it out of the way. Remember this thing pre-equal 3, Sn, permutations, right? I would point out that the three four things. First of all, what is a permutation here? What does that mean? It's a bijection on what? The numbers 1 through n, right? That was our definition of permutations. There's the set of one-to-one and onto functions from the set of numbers 1 through n to the set of numbers 1 through n. I mean, there's a more general concept of permutation we'll get to, but for us, that's Sn, the so-called symmetric group. And so a couple of important properties. One is closure. In particular, if we have sigma and beta in Sn, then sigma composed with beta is also an element of Sn. All right, so if you take two permutations and you compose them, you get another permutation. And then these three, beyond closure, we have these three properties, which I would number like so. I would point out that function composition is what? It is associative. Function composition, there exists an identity, which we could call epsilon. Sometimes I call it id n sub n, which is kind of an annoying, very cumbersome notation. All right, the identity, what's the identity do? Identity composed with sigma is equal to sigma composed with the identity for any permutation, right? That's the identity permutation. And then, last but not least, the inverse of permutation is a permutation, right? In other words, sigma in Sn implies that sigma inverse is also an element of Sn, right? And in pre-equal 3, I explained to you how we can actually calculate that in terms of cycle calculations, right? So this is sort of the basic fundamental example of a group, right? The set of permutations. And like I said, that was what Galois was studying, these permutation groups of roots. And for the most part in the 19th century, group theory was the study of permutations. But in the late 19th century, mathematicians, I think it was Dike, in some paper about tessellations, introduced a more formal definition of a group, which we know and love today. And so I'll state that for you. Here it is. Definition: a set G, all right, with an operation. Now, I could put the word binary in here to be more precise, if you know what that means. A binary operation, which I'll call star here. The binary operation goes from the Cartesian product of G with itself back to G again, forms a group. All right, if the following axioms hold, right? Number 1, we have associativity. Number 2, we have identity. And number 3, we have invertibility. Invertibility, if I can spell today, that'd be great. All right, so let's be more precise. What's that mean? Associativity means that I'm going to trade my star for an asterisk because I can do those better. But I'm still going to call it star. A star B star C makes sense in the sense I'm writing down right? Now, to be more precise, what I mean I can do this, or you can do that, right? You can go with this, or you can go with that. That's associativity. In other words, you don't need parentheses for products of more than two things, right? Identity is that there exists E in G such that G times E is equal to G is equal to E times G for all G in the group. And then invertibility is X. Well, let me say it this way: if G is in G, then G inverse is in G, where G times G inverse is equal to E, which is also equal to G inverse times G. Now, this, I'm being redundant, okay? If you want to read a more minimalistic statement of the definition, you could look at Rotman's book, Elementary Abstract Algebra. He does things like, he has a definition which just uses like the left part of the equalities, and then he proves that the right part of these equalities automatically follow. I'm just giving a slightly less than minimalistic definition because I think it's better pedagogy to tell you this is what happens for a group. This is what has to happen, all right? All right. So there you go, associativity, identity, invertibility. And then finally, and this is more, if A times B is equal to B times A for all AB in G, then G is abelian. Well, to be more clear, G is an abelian group. And that, of course, is in honor of Abel or Abel, depending on where you're from. All right, if there exists, on the other hand, even one pair in the group A comma B such that A times B is not equal to B times A, then the group is said to be non-abelian. Right? Non-abelian does not require that all elements don't commute. It just requires one pair of element doesn't commute. That's enough. One rotten apple makes all the apples non-commutative. Non-abelian. We also say non-commutative. All right. Any questions so far? Now, the notation I've been using here for the definition is star. All right? But as we go on, there's a couple different notations we'll use for the operation in the group, right? So basically, here are the options that we tend to use. A lot of times, instead of writing A times B, we'll just write AB. This is called juxtaposition. All right? Just write the elements next to each other. That denotes the group multiplication. All right? That's often the notation we'll use for proofs and things because it's not annoying. All right? The other notation sometimes we use is A plus B. This is so-called additive notation. All right? So we have additive notation, and we have multiplicative notation. Both A star B and AB would be examples of multiplicative notation. All right? Traditionally, if you use additive notation, unless you're just kind of a weirdo, sorry, judgment call, but people who use additive notation for non-abelian groups, those are perverse people. It is usually the custom of mathematics that if we use a plus, we're thinking about an abelian group, all right? A group where the operation is commutative. And so it's kind of built in. If you say you have an additive group that is, by assumption, an abelian group, all right? So what are some examples? Tons of examples, right? How about the integers with addition? So, by the way, for a given point set, you might have different operations possible, right? So this can also be summarized. The group we might write as a pair, G comma star, right? Because a group is two things. It's a set and an operation which satisfies these axioms, right? So to more concretely and precisely describe a group, we should say it's a pair, right? It's a set with an operation. So the integers with addition forms a group, right? Because the usual addition of integers is what? Associative? Right? Is there a 0? Yeah, I mean 0 is the identity, right? The additive identity. So here, E, quote unquote, is equal to 0, right? X plus 0 is equal to X is equal to 0 plus X for all X and Z. I'm not going to write it all out, but integer addition, of course, is associative. Every integer has a negative, right? The negative is the additive inverse. So we have that. We also have that language, right? If you're using multiplicative notation, the inverse is said to be a multiplicative inverse, right? If you're using additive, we often call the additive inverse the negative of the element, right? Okay. How about a non-example? What about the integers with multiplication? Integers with multiplication. It's associative, right? There's an identity. 1 times any integer is the integer again, right? It's associative. It's got identity, right? But what's the problem with integers under multiplication? Inverse, right? What integers have multiplicative inverses? Just 2. Right? I mean, you have to solve the equation xy equals to 1. That would make x and y multiplicative inverses in the integers, right? What are the solutions to that for integers? 1 and -1, right? So 1 is its own inverse, and -1 is its own inverse. That's it. There are no other integers which have multiplicative inverses, right? 2 has what's the inverse of 2? In terms of integer multiplication, it's 1/2, right? But 1/2 is not an integer, so we're out of luck. On the other hand, if we look at the rational numbers with addition, with multiplication, is that a group? We're still in trouble. What's the multiplicative inverse of 0? 0 times what gives you 1? Can't do, right? So to make this work, what we have to do is throw out 0. So this is what this notation means. Q with a upper X on it, that's rationals, Q and Q, such that Q is non-zero. So the set of non-zero rational numbers under multiplication does in fact form a group, right? It's what's called the group of units for the rational numbers. And of course, you could just as well put real numbers, non-zero real numbers under multiplication, or non-zero complex numbers under multiplication. These are all examples of multiplicative groups, right? By the way, the rationals, the reals, the complexes, these are all additive groups. What's the identity for the additive group? What's the E? What's the identity here? It's not complicated. You tell me? 0, right? 0. All right, so to have a group, we need an associative operation that's closed, that there's an identity, and every element in there has to have an inverse, right? Another greedy example I could give you would be any vector space under addition, right? You all had Math 321. You know what a vector space is. A vector space with respect to addition forms a additive group, right? Where the 0 vector is the identity. Now, moving along here, another example, which is more interesting, is GLNR, the general linear group, all right? And what is this defined to be? Well, you said group is in its title, so it must be a group, right? That's not a proof, right? You can't do proof by labeling. It's not allowed. So n by n matrix in the reals such that the determinant of A is not equal to 0, right? And the group operation is going to be what? matrix multiplication. Remember that? So if you have two invertible matrices, is its product invertible? Right? If you have A and B in GLN, then what's the determinant of AB? It's not an easy thing to prove, but the determinant of the product is the product of the determinants. Right? And so if those are both non-zero, it follows that the determinant of AB is non-zero, which says what? Therefore, what? AB is also an element of GLNR. Well, that's good. That means that GLNR is closed under matrix multiplication, right? Then what else do you need? You need that matrix multiplication is associative. It is. Yay. We know that from linear. And how about inverses? If the determinant's non-zero, is the inverse, is the determinant of the inverse non-zero? It is, right? So it's closed under inverses. And the identity matrix is in there, so that's a group, right? That's a pretty interesting group. It's non-abelian, and it's infinite, right? In fact, these were all infinite groups, right? Now, the SN, the set of permutations, in contrast, is a finite group. How many permutations are there on n symbols? How big is that group? What's its order? What's its size? What's its cardinality? You can tell me? How many bijections are there on n elements? Oops, sorry. I do try to give you more time than that. It happened before I realized it, sorry. You can look at the video later, I think, yes, I'm sorry. The answer to the question I just posed is n factorial, all right? The size of the group of permutations is n factorial, right? Or n! No? Sorry. I tried. It's been a long summer, huh? All right, theorem. In a group G, there can be only one. It's the Highlander theorem. Okay, fine. Identity element. That kind of ruins it. Let's prove it. Suppose E and E prime, suppose E and E prime are both identity elements for G with operation star, all right? Then we know that E times E prime is equal to what? Remember, the definition of the identity is what? It's equal to E, right? But that's also equal to what? E prime times E, right? Which is equal to what? Equal to E prime. Yep. Yeah, so we're done. Okay, great. That one's not especially exciting. Now, although that's a suppose, by the way. That's the kind of symbol I use when I can't get the camera to start at the start of class. Sorry about that. You notice we didn't use associativity, right? So apparently we could look at something that was like a group, but drop the associativity axiom and still have uniqueness of inverse, right? So for those of you who are mathy types, hopefully that's all of you, you might wonder, you know, could we drop some of this structure and still have something interesting? The answer is yes, and there's a variety of different ways to do that. I have included this lovely table of such things, which I stole from Wikipedia. Such things as semi-category, category, groupoid, magma, quasi-group, loop, semi-group, monoid, group, and abelian group. Now, I don't expect you to know all these, but it's kind of interesting to look at the various weakenings of this definition and how the different uniqueness properties of group play out. Like the next thing we're going to look at is cancellation laws, right? Which I think I'll put here, theorem. Cancellation law. And here it is. In group G, the right and left cancellation laws hold. All right, so in particular, that is if BA is equal to CA, then we get B equals to C. I'll call that 1. And then 2, if AB is equal to AC, then B is equal to C, right? I suppose the first one is right cancellation and the second one is left cancellation, right? I mean, correct? Why is your name Stephen? I mean, I have issues with this kind of, I mean, I'm not joking. Like, there are times when left and right are used in exactly the opposite way, I would think. But anyway, they're just labels. Those are cancellation laws. Whatever handedness you'd like to ascribe to them. All right, so let's look at the proof of that. So let's see, assume that A, B, and C are in G with BA is equal to CA, right? By the way, what's the operation for the group? What am I using now? I'm using juxtaposition, right? So you're like, well, and so this is one of those things. Like you could give this proof in using a star notation if you wanted. But I'm going to use juxtaposition this time, all right? All right. Then A inverse in G exists by axiom, what is it? 2. Hence, multiplying by A inverse on the right we find what? B A inverse is equal to C A. I'm putting some parentheses in, guys, inverse. But then what? By associativity, what does that give us? B A inverse is equal to C A inverse, right? Using associativity, then what does it mean for it to be the inverse? Well, that's the identity, right? So that implies that BE is equal to CE by definition of A inverse, right? And then what? By definition of the identity, that just gives us what? B equals C. So that concludes the proof of right cancellation. Yeah.
And that was axiom. Is that axiom 3 that you used the inverse? I'm just wanting to make sure that I did not miss something.
2. The existence of, oh, yeah, 3. Why did I write 2? Sorry about that. Okay, so left cancellation is proved in much the same way, all right? So I had something I wanted to show you before class was done. Everybody got that? Every proof that's in this particular section of my notes, you would like to be on the test, right? I mean, give or take. I mean, they're not bad. The one that's a little bit more subtle is the Laws of Exponents. Sorry, I was trying to write all these out, but I've gotten a little bit behind, and I want to make sure that we start. So what I'm going to try to do, guys, is I get this bad habit of trying to cover the last bit of one lecture in the next. And so what I'm going to do this semester is I'm just going to go on and let you read so that the next lecture is not ruined by my inability to finish this one properly. I think we'll all be happier that way. But all is not lost for this lecture yet. Give me a minute. If I can. Does it show up? Oh, it showed up. Yay. All right, so we just proved the uniqueness of the identity. Here's that lovely table I was telling you about a second ago. Give me a second here for the lighting. There we go. That'll be better. Something I always forget to do when I do this is to readjust the zoom because otherwise you can only see part of it. There we go. All right, so I got this silly stuff out of my system. Here we go. That was the cancellation law. We just proved that one here. That remark, the point of that remark is, you know, by doing this proof about the cancellation law based on that axioms, we've just shown that cancellation holds for any group, right? There's hundreds of examples of groups that one proof works for all of them. That's part of the power of abstraction, right? It's a very efficient method of argument. The next theorem is uniqueness of the group identity, all right? So suppose you had, uniqueness of the inverse, rather. The inverse in the group has to be unique, okay? So if we had G with two inverses, H and H prime, suppose they're both inverses for G, that means that GH is equal to E is equal to HG, and also GH prime is equal to E is equal to H prime G, right? But then, that means that we have GH rather, is equal to GH prime. So by the cancellation law, right? Which cancellation? You tell me, Stephen. I'm just messing with you. By left cancellation, we get H equals to H prime, right? 50-50, right? I mean, if you're in doubt, just say by the cancellation law. I won't know the difference. If you just say by the cancellation law, you're safe, right? Am I really going to take points off if you just said left versus right? I mean, probably not. All right. Next up, and this is kind of important, powers, all right? Exponential notation. So like a group element to the 0 power is defined to be the identity. Then we define other powers recursively, like g to the n plus 1 is g to the n times g for positive n. And for negative powers, we define it to be powers of the inverse. All right? So this is just the standard definition for powers that you've learned for numbers. It's also true for groups, all right? And on the other hand, if the group is additive, 0 times g is defined to be 0, and n plus 1 times g is defined to be ng plus g. So the question, additive groups, we repeatedly add group elements together. That's the analog of the power. And likewise for negative, we define it by repeated subtraction. Long story short, we have laws of exponents. G to the m times g to the n is g to the m plus n. And then g to the m to the n is g to the mn. All right? In additive notation, that is mg ng equals to m plus ng. And also, if we add m copies of g n times, that's the same as just adding mn copies of g. Trust me when I tell you, to actually prove these things, it is unpleasant. It would easily eat a week of our time. There are many cases to consider. If anyone tells you otherwise, they're lying. I know, because I made this a homework inadvertently once, and then I had to write a solution for it. And it was unpleasant. All right. So finally, sorry to rush this, but I'll be brief. The next concept, of course, is a ring. Actually, many of my examples also have a notion of addition as well as multiplication. And when you put those together, you get what's called a ring. Most of the things you know are rings. Goodness gracious. Silence. All right. We're going to assume our ring has a multiplicative identity. A ring is not a group with respect to multiplication because it's got 0 in there, and 0 doesn't have a multiplicative inverse. If the multiplication commutes, it's said to be a commutative ring. Integers are the quintessential example of a commutative ring. Sets of polynomials are commutative rings. For us, you're like, well, when are we going to get to a ring? Well, today, in this sense, there's the definition for you. We're going to be focused on groups, right? But I always tell this class, you know, you've heard ring by spring. For us, it's ring by October. Okay, so something like that. Rings were studied in great depth in the early 19th century. For example, Emmy Noether and her school made great progress to abstract algebra. And finally, the other main application of group theory that I've been interested in as a student was this. These are what are called group representations. What's a group representation? It's something we find in quantum mechanics. It's a homomorphism of groups onto operators which act on quantum states. But long story short, pictures are group representation theory. And if you look at these pictures, they actually explain how you can build. And these pictures you can understand at a certain level. They'll explain how you can actually build neutrons and protons by tensoring what are called quark states. So this mathematics actually explains the inner workings of protons and neutrons as they appear from quarks. And that's all group theory that physicists think of. Now, group theory for us is something less out there. But this is another main motivation people have to study group theories. It's widely used in modern physics, all right? That's probably not a motivation for you. If you'd like to know more about that, you can ask our physics department. So thanks. See you guys next time.